Hello guys, welcome to this new video on deriving the formula for time dilation. So today I'm kind of demonstrating this experiment where you have a spaceship going across the sky and you have two reference frames. One is inside the spaceship, which we are going to call S, and one is the reference frame of the observer, which we are going to call S prime. Okay, so simply put, we're just going to move the spaceship across the sky, and using observations we make during this movement, we are going to be able to derive the formula for time dilation. And once we get that, I'll demonstrate a few examples and talk about why time dilation is useful. So moving right into it, here we have reference frame S, where we have a mirror, we have a light source, and the entire point we're going to do is reflect a beam of light across the mirror. To get an incredibly crucial point of information from this scenario, we need to find distance, d, which is simply found by multiplying velocity times time. So, as the velocity of the light beam is c, the speed of light, the distance it's going to take is the speed of light times t, the time it takes for the light source to hit the mirror. Moving on to our next reference frame, S prime, we have an example here, a depiction, where we can see the spaceship moving across the sky. As the light reflects from the view of the observer, it will appear as follows, where the light source, although in the spaceship it is simply moving up and down, from the reference point of the observer, it is moving at an angle. The distance between two of those frames is simply put d equals v times t prime, where v is the velocity of the spaceship and t prime is the time it will take for the event to occur from the view of the observer. Then, the distance it will take for the light to hit the mirror will be found in d equals c times t prime, where c is the speed of light, and t prime is again the time it takes for the light source to hit the mirror from the point of the observer. Now, I'm sure as you can tell, it is incredibly close to a triangle already. We still need that right leg, so we know the right leg from the spaceship reference frame. So we're simply going to create a triangle where c times t prime is the hypotenuse, c times t is the right leg, and v times t prime is the bottom leg. And using Pythagorean theorem, we can find that ct prime squared is equal to ct squared plus vt prime squared. So using this formula, we're going to simply change it and find the value of t prime, and that will give us time dilation. So here we have our starting formula. First things first, we're going to expand it just like that, which is going to be incredibly crucial to the next step, where we're going to subtract v squared t prime squared from both sides. Now, as I'm sure you can see, we have a t prime squared on both sides, so we can simply factor that out. Once we have this all factored out, we are going to divide everything by c squared, and that's going to give us this, t prime squared times 1 minus v squared over c squared equals t squared. Now, we're just going to divide 1 minus v squared over c squared on both sides to get t prime squared equals t squared over 1 minus v squared over c squared. Now, as I'm sure you guys can all figure out by now, to get t prime, we simply take the square root of both sides, and that will give us our formula. T prime equals t over the square root of 1 minus v squared over c squared. Using that, we know that the Lorentz factor is 1 over the square root of 1 minus v squared over c squared, so to finally simplify it, we will get t prime equals gamma, which is the common denotation of the Lorentz factor, times t, where t prime is the time it takes in the reference point of the observer, and t is the time it takes for the event to occur from the reference frame of the spaceship. Now, we have this formula, but we don't know quite what it does. So here's an example that will show the functionality of this derivation. Here we have our formula, t prime equals gamma t, and we're saying that the velocity of the spaceship is equal to half the speed of light, c over 2. Plugging that in, we will get t prime equals t over the square root of 1 minus c over 2 squared over c squared, where c over 2 is simply the velocity. You guys can plug this into your calculator, but evaluating this expression, we will get t prime equals t over the square root of 0.75. And evaluating the expression once again, we will get t prime equals 1.1547t, which we can then plug in any value we want for t and find t prime. All right, so in this example, we will plug in 60, where in seconds, essentially saying in a minute on the spaceship, what is the time on the ground? And by simply multiplying that 60 seconds by our constant of 1.1547, the Lorentz factor, we can find that if we spend a minute on this spaceship, or our clock registers it as a minute, on ground, we will have 69.282 seconds passing. Of course, this is pretty exaggerated. We're never going anywhere close to the speed of light, but this really demonstrates just how drastic this can be the closer you get to the speed of light. When the speed of light is reached, time is infinite. All right, so you might say that this is a bit abstract, this is a bit theoretical. How is it actually used? Does this actually matter? Or is it all the pointless physics we've all learned? And the answer to that is it is incredibly crucial. If you look at a synchronization of clocks, GPS uses this time dilation equation. The ISS must use it because synchronizing clocks is incredibly important for a series of operations. And if you don't do this, although it's very minimal compared to this example, is millionths of a second, it doesn't really change a lot often, but still every few days they have to synchronize their clocks because of this time dilation factor, and hundreds of experiments have been done proving this time dilation property to be true. So that's the end of the video. I hope you learned something. I hope you found a new interest in physics, and I will see you all in the next video. Hope you have a great day.